Okay, our topic for today is equilibrium in three dimensions. Now, we already discussed this for point objects, but now we're going to look at extended bodies. And previously, when we did point objects, we only had to consider the forces summing to zero. Now, we're also going to consider the moments summing to zero. And we're going to add in a few other structures. Um, Something called a ball and socket joint. There's a socket there that holds the ball in place. And this spins freely in all directions. So there's no way it can resist a moment, but it can resist a force in all three directions. So you can have X, Y, and Z components of reaction at a ball joint, a ball and socket joint. Okay, let's do an example. So here we have a square plate. It's 500 pounds of weight. It's supported by a ball and socket joint at the origin that we can't see. It's supported by a roller here at the point B. You have this in your notes. And by this rope. Okay, and there is a couple moment acting on it in the positive k direction. Our first task is to draw all the forces that act on it. So weight was mentioned, so there'll be a weight force acting here at the center of the plate. This is a roller, so it can only exert an upwards component in the z direction. And we could have, at this ball and socket joint, potentially z and y and x components of reaction. There will be a tension here in the rope. So those are all the forces that act on the plate. I guess we could label these. This is weight. We'll just call this force B. And then I'll just call this a Z. Oh, bother. All right, so where was I? So yes, components along the Z direction, the X direction, and the Y direction. Okay, and this is tension. And then we've got the couple moment up here. So these are all pretty easy to express as Cartesian vectors. Tension will need to do a little bit of work. So first we'll have to find the unit vector along the rope just by doing final minus initial over length. So tension going this way, we'll select this is our final point that has coordinates 0, 3, 4. The initial point here down in the plane, um, so we see that it's an 8 by 8 square plate. So this is 8 feet over and 3 feet in the I direction. So that's 3, 8, naught. And then we need to divide this by the length. So this is just going to be negative 3. Okay, so yes, final minus initial. So not 3, 4 minus 3, 8, 0 over the length. And so that is negative 3, negative 5, and 4 over root of 25 plus 9 plus 16, that's root 50. So that's the unit vector. And then the tension force vector will be T times each of those components. You can keep it exact or you can write it as a decimal. I'm not, so this would be like minus 3 over root 50. As in decimal form, it's 0.424. This would be 5 over root 50. That's 1 over root 2 if you simplify. And then 4 over root 50, positive 0.566. So those are the three components of tension in decimal form. Now we're also going to need the moment of tension. And so remember, we can use any r vector from the pivot, which is the origin, to the force line. So we could use this as an r vector, or we could use this as an r vector. Let's call this up here the point C, and then I will use ROC from the origin to the point C crossed with the tension vector to find the moment about the origin for the tension force. So we'll load this up and we'll do the determinant technique. So we'll have I minus j and k. So the components of r, it's 3j plus 4k. So you load the r first, 0, 3, 4. And then for the tension, we can probably work a little more easily if we use the exact values here. So that would be t over root 50. I'll just pull that out. Have to remember to multiply that at the end. And of course, this is just 5 root 2. And then it's minus 3, minus 5, and 4. So we have to do this cross product. So for I, you cover this, and it's 12 minus 20. So that's 32I. You cover this, it's nothing minus 12. So that's 12. But then there's a negative that's attached to the j, so that's minus 12j. Then you cover this, it's nothing minus 9, or it's plus 9 in the k direction. Now, if you had loaded in the decimal values here instead, then you'd get the same thing. And I'm just going to write this with the decimal values here. This works out to be 4.525. This is minus 1.697. And then the k-coordinate is 1.273. Okay, so whichever way you want to do it, it's fine. It really doesn't make the math any easier one way or the other. So we've got the force diagram completed, and we've got these things worked out as Cartesian vectors. Now we need to do that because we're now on the next page. Here's the force diagram all done for us, by the way. We're now going to apply the static equilibrium conditions, which simply said forces sum to 0 in the x and y and z, and moments sum to 0 in the x and y and z. So for each force, we'll just use this convenient chart to load in the components. So we'll start with the force A, where we had an unknown x, an unknown y, and an unknown z. And those three acting at the origin give us no moment. Next, we consider the force B, and it was a roller, so it doesn't push in the x or y direction, it just pushes in the z direction. Now, for moments, a force pushing up at this point, we'll use the scalar technique. There's going to be a moment about the positive x direction, where the perpendicular distance is 4 feet. So this is a positive x moment of 4bz. Pushing up in this direction also rotates you about the negative j. And the perpendicular distance there is just the entire width of the plate. That's 8 feet. So this is a negative y moment, negative 8bz. Now, of course, you can do that using the cross product technique. You could do 8i plus 4j crossed with b in the k direction, bz in the k direction. You'd get the same result. But the scalar technique is faster. Next, let's consider the weight force. So it acts in the negative z direction, so downwards 500. And pushing down in the center of the plate gives you a negative I moment. Now, the plate's uniform, so this will act in the middle. That's 4 feet from the x-axis. So it's a negative x moment. There's also a y moment. If you push down on the plate, it's going to rotate about the positive y-axis. It's again 4 feet away of perpendicular distance. And there's no z moment, so this is positive. 2 more things to go. First of all, the tension force. So again, it doesn't really matter. You could put in the decimals or you could put in the exact. I might just put in the exact. So, and root 50, I'll just write it as 5 root 2 here. So that's the x component. Here's the y component. We're just recopying this from the previous page. Those are the components of force. And then here are the moment components. It was root 50. Root 50 simplifies to 5 root 2. So we've loaded those components in. There's only one thing left to do, and that was the couple moment. Now, couples are not associated with any force, but there is a z component, an unknown couple. And so there you have it. Conditions for equilibrium tell us these sum to zero, these sum to zero, and so on and so on. Now, as we look at this, we see, holy smokes, this is like, what have we got there? 1, 2, 3, 4, 5, 6 unknowns. That could be like a 6x6 matrix. Fortunately, the equations decouple. If you look at these two equations here, you'll see it's two equations and two unknowns. There's just Bz and tension in these equations. And so we should be able to solve that. So if we just recopy out those decoupled equations for Bz plus 32 over 5 root 2 tension, and you can solve these using technology. And again, in the midterm, this would be, as difficult as it would get. Right? So, as a matrix, this is 4 minus 8. And then these two numbers here, augmented 2000 minus 2000. So you could solve this using your matrix techniques. You could solve this using Wolfram alpha. There's lots of ways to go about doing it. This is easy enough just to do by elimination. Okay, if this is row 1 and this is row 2, all I'm going to do is 2 row 1 plus row 2, and then that's going to eliminate the Bz. And then I will have 64 minus 12, I'll have 52 over 5 root 2. And I'll have 4,000 minus 2,000. So it's going to be 2,000. And I said 64 minus 12, that's 52 over 5 root 2, which I cross multiply. And so this will be the value of tension. So that's 271.964 pounds. Bz can then be found. It's going to be taking this equation, dividing by 4, it's 500. And then dividing by 4, that'll, from the 32, that'll just be 8 over 5 root 2 times this value of tension. And computing that, solving it, it's 192.31 pounds. It then remains to back substitute for all of the other values. You can show from the last equation that the moment is minus 9 over 5 root 2 tension. You can solve for AX using the X force equation, AY, and AZ in similar manner. AZ is the one that requires the other unknowns, so it's the last one that you can do. So it's good to show the math to about this level of detail, because if you just write down the answers, if they're wrong, then I don't know what you did, and I can't give you partial credit. So there's a complete solution to the problem. So that took us, what, about 10 minutes? The force diagram and the equations takes, that's 25% for the force diagram, 50% for getting the chart set up with the correct equations, and then the last 25% solving it and getting the correct numbers. But that's all we're going to do today. Let's try another problem. Here, we've got a vertical pole, like a flagpole, a couple of cables, stays, and then there's a load being applied on an angle. So stop the video, produce the force diagram, and express these forces in Cartesian. So that should just take you a couple of minutes. So just pause and do. Okay, so let's see. Have a look at how you did there. So first of all, for the forces, we've got two tensions here. I guess we'll call them tension 1 and tension 2. Now there's a lot of symmetry in this problem, and we did something like this before. Given that this force is in the YZ plane, we're expecting these two tensions are going to be equal, and we're expecting that this force is going to be 0. And indeed, that's going to emerge from the equations. But for now, let's just call them T1 and T2. Okay, so here's the T1 Cartesian vector. The T2 Cartesian vector will just be the same with a minus I direction. So check your forces, make sure those are right. If they didn't work out right, check that you had the correct final and initial divided by the length. Now here, there's no value in keeping it in exact because you end up with, the square root of some decimal number anyway, which isn't useful to carry around. This force is easily enough. We'll just call this one F, so its components are pretty easy, and this is just going to be AX, Y, Z again. Now, for the moment, remember, you can go from the pivot point to the force line. So you could go here for the moment of T1, but it's easier just to go straight up, because that gets you to the force line and only has one component. So that's why I say use this R vector. So again, I did it with the the determinant technique. So the T1 gets pulled out in front, and there's the moment of T1. T2 will have the same moment, except negative in the J direction. So let's see if I can get all that on the screen at once. Take a sec and just make sure that's right. Then we'll load it up in our chart and have a look at those equations. So check, then load in chart, and then we'll look again. Okay, so components of AX, components of tension and force. We didn't mention that earlier, but it's got a Y component, which is positive 550 cosine 15, and a Z component, which is negative 550 sine 15. For its moment, there's only an X moment. You just go straight up for the R vector and then cross it with the force. It's a negative X moment. The perpendicular distance is 2.5 meters, and then the perpendicular force is the 550 cosine of 15. Sorry to squeeze that in there. Okay, so those are our conditions for equilibrium. So right here from this equation, we can see that T1 is going to equal T2 because these two sum to 0. So that means T1 equals T2, and let's just define that as being the tension T. If the tension T, T1 and T2, is the same, then you could see that these wipe each other out, and that leads directly to the conclusion that AX has to be 0. So that simplifies our analysis a little bit. Now we can use this equation because these are both T, and then we just move this to the other side and we divide by 2 times 0.246. So solving that equation, so it would be 2.5 times 550 cos 15 divided by 2 times 0.246. So that gives me 2702 newtons for the tension force. Once you know the tension force, you can solve directly for AY and AZ. Solving for AY, well, you could see it's 2 times 0.082 tension minus 550 cos 15. So it actually ends up being negative no harm done there. That just means that the ball and socket joint is actually pushing in the negative Y direction, and it's 88.5 newtons. And then the Z component you get by, it's going to be 550 sine 15 plus 2 times 0.983 T, and that works out fairly large. That's 55 newtons of force. All right, now at this point we'll introduce a couple of other structures that will sometimes come up in our problems. Here's a collar, so it's free to slide along this axis. This is a smooth axis, and it'll rotate freely around that axis, but we won't do a problem on that one just yet. Here's a thrust bearing, so the rod will slide through easily. It's smooth in this direction, and it will spin easily around that axis. Here's a hinge. This is the one we'll look at in our problem. Now, the hinge can't resist a rotation in this direction. So you can't possibly have a reaction moment. On this axis, this would be, you can't get an mx moment. it does depend on which way the hinge is oriented. For instance, here, I think that's the x-axis, and so you couldn't have a y moment from this hinge. Now, you can get moments in other directions. If you try and rotate this hinge about the z-axis, it will react. There will be a reaction moment. Similarly, if you try and, say, push this side up and this side down and rotate it around the y-axis, it will also resist that. All right, let's try an example with the hinge. Now, this diagram sometimes gets mangled by Microsoft Word, so let's just take a second and make sure that we all get a good copy of this diagram. So it is a square plate. Here's a hinge supporting it at the origin. There's a rope which goes to this corner, and then there's a strut AB. So our first job is to do the force diagram, and then we will find everything in Cartesian, and then we'll apply the conditions for equilibrium. So this door is going to be pushing down on the strut, so there'll be a strut force along the AB axis. Okay, so other forces. There's the tension force here. So given that the door has weight, the string's going to be pulling up from C towards D. It's kind of not cooperating very well there. Okay, let's leave it like that. Okay, other forces include, let's see, the weight. That'll act in the center. And you could see this is symmetrically placed on both sides of the y-axis, so the weight vector will act along the y-axis. And then at the hinge, so the hinge will exert reaction components in the z, y, and x direction. And we're told that the hinge may not be properly aligned, so there could potentially be some reaction moments here. This hinge won't be able to resist a rotation around the x-axis, so it could not give an x reaction moment, but it can certainly resist z rotations due to the screws that are holding it in place, and it could certainly resist y rotations. More on that later. So there's our force diagram. We need to express the tension vector and the strut vector in terms of their components. So we'll pause the video, you'll find those two forces in components, and then find the moments of those two. Then we'll check back in a bit and see how you did. Okay, so let's see how you did. For the tension, you need the unit vector, so again, final minus initial over length. So the length ends up being root 110. So I'll just keep that as an exact value. Now for the moment, we have to go to anywhere on the force line. You could have gone to point C. I choose to go to point D. So that's just 3.5i plus 7k cross the tension force vector. So I pulled out the t over root 110. So this is the exact value. And then in decimal form, that's the moment of tension. So check how you did there. Next, for the strut, you again need the unit vector. And when you do final minus initial, you find you're going 2.5 in the positive I, 4 in the positive j, and then up 4. So divide by its length, which is the root of 38.25, and you get this for your unit vector. So there's the strut compression force in terms of the unknown FAB, or force. We have to go from the origin to the force line, so I just went down to the point A because that just has a negative 4k component, and that makes the cross product easy to do. Don't use the determinant technique there. We'll just use the little triplet I, j, k, so that k cross I gives you positive j, but then there's a minus there that makes this a negative. Then k cross j is negative I, that wipes out this minus, and you end up with this. So there's the moment. And now we're simply going to load up the chart and then solve the equations. So let's just do that together. So at the hinge, we had, oh goodness, I'm still thinking A there. We had hinge x, y, z, and no moments, because they act at the pivot. We had a weight force, which is downwards 500. Now, that just acts on the y-axis, so this is only going to give us an x moment, and it's going to be a negative x moment. So it's a 5-foot square plate, so it's 2.5 feet out to the force of the weight vector. So have a look there. So that's 2.5 feet because it's a 5-foot square plate. And you can see clearly from this picture that's going to be a negative I rotation. Okay, then we have the strut force. I'll probably drop the AB and just call it F. And we found its force components. So we're just loading these up from the previous page. And then we found its moment components. And then nothing in the Z direction. So now let's load up the components of tension here. Now, if you look at those equations, you'll see they don't have a consistent solution. Because this equation, if there were no reaction moments, would just tell us the tension's zero. If the tension's zero, that would tell us the force is zero. And that's not consistent with this equation. So clearly, there must be a reaction moment because the hinge is not properly aligned. So we must have a Z reaction moment for a solution. Now, a Y moment is not needed. So you make minimal assumptions in order to get a solution. So this Y moment is not needed for a consistent solution. So we assume it's zero. And we said earlier the hinge cannot resist an X reaction moment. Sorry, it cannot resist an X rotation, so there cannot be an X reaction moment. All right, so now we proceed to solve these equations. So this equation here gives us a relationship between force and tension. Again, this is just two equations and two unknowns. So we know that the force will be 1.668 over 1.67 times T. And we could substitute that into this equation and then proceed to solve directly. So what we find is the tension is 208 pounds. The force F is 214.6 pounds. Then we solve for the reaction moment Z, and we find that it is 347 foot-pounds of moment. And then we solve for the hinge reaction components as well. All right, so this is, although it's not especially difficult, it's just a bit perhaps uncomfortable the first time through. You know, you reach a certain point, then you see it seems like you have to start making assumptions. I mean, we were guided in that way because we were told the hinge might not be properly aligned, so we knew this was zero. And then it comes down to the possibility of these. And so you just sort of make the minimal assumption that you need to in order to survive, which is that you have one of these, but not one of these. Nonetheless, I realize that that's sort of uncomfortable for students, so I generally give you some pretty strong indication about which moments exist. If you look back to the first problem, I did that when I told you that there was a Z reaction moment. So that's pretty typical of the way that we will proceed. So henceforth, you'll be told if there are reaction moments present in the supports, and if the system is properly aligned, then that's your indication that there are no reaction moments. All right, so we're building up some momentum at this point. And so now we're pretty much just going to hand you a problem. And this one I want you to work on in groups on the whiteboards. Start with the force diagram, then check that with your neighbors. Then build your chart. And at that point, we'll play the video and you'll see how you did. Then solve the equations. So here we've got what's called a thrust bearing. Sorry, a journal bearing, and here's a thrust bearing. So now let's just quickly go back and just discuss those very briefly here. So this journal bearing, the rod travels through it. It's smooth, so it cannot resist a force in that direction. So there could not be an Fy here, but there could be potentially a Z, and there could potentially be an X force that act at that point. So no Fy. Similarly, it's going to spin really easily around the y direction, so it couldn't produce a y moment, but there could potentially be, if it wasn't properly aligned, a z moment or an x moment. Now, in the example that we're about to do, we're told that it's properly aligned and supported, so there won't be these two reaction moments, but there will be these two reaction forces. So the rod is going to have weight on this bearing, pushing down on it, so the bearing will push up with a Z force. And I think there's also a sideways force on the rod, and so you get a sideways reaction in the x direction. So here I said that you should do the force diagram yourself, but because this is the first one of these you're doing, I'll just tell you at B, there is a Z force and there is an X force. There cannot be a Y force because it slides through smoothly. Then here at A, this is a similar bearing, except it's got a back to it, so it can actually push out. So there can be a Y force there, and a Z, and potentially an X as well. There are no reaction moments because these are properly aligned, and there's no reaction moments here. So there's the force diagram. Let's just label that. So we'll call this one the Z at B, this is the X at B, and this is the point A, Z, Y, X. Okay, so the force diagram is complete. We did it together. So you guys now fill in the chart, and then we'll compare notes. Okay, so forces and moments. This is a little tricky. This moment here is going to be 3.5 feet away, so that'll be a negative I moment, and then 2 feet away for the J moment. Here, this force straight down, here's its line of action. You could see this is going to rotate around the negative J, but pushing down here, the whole structure is going to tend to rotate this way. That's a negative I moment. So there's actually two moments of this force. You could just do R is 8J minus 3 cos 30I, and then you could take the cross product with F. That would be another way of doing it. So you could use your R vector is 8J minus 3 cos 30I, and then just cross that with the force, which is F in the minus K direction. So here's the chart. Scroll down, check and see how you did. And then check your answers. Okay, so again, we should be getting pretty good at this. Let's try just one more for today. Here we've got, again, here's a journal bearing, here's a thrust bearing. So we learned about those force diagrams. Then there's a couple of pulleys, and there's forces acting on the pulleys. Here's an unknown. Here's an 80 positive K, 60 in the negative I direction, parallel to the x-axis, and 40 in the negative I direction, also parallel. We're given the radius of this pulley, so you could see there's going to be like a K component to the R vector and a minus K component there, if you like. And similarly, this has a radius of 1/3 of a foot, so this force acts sort of out here in the plane, right? It's got an X component and a Y component. Okay, so the force diagram, you've got to add forces here at A and B, and then load it up in the chart. Give that a try, and then we'll compare notes. So force diagram. So this journal bearing will have a Z component of reaction and an X component, potentially, and because they're properly aligned, there's no reaction moments. Here, for the thrust bearing, it could be pushing back with the Y component, and because it's properly aligned, there's no reaction moments. When we go to find the moments, as I mentioned, say for the 60-pound force, we're going 2J plus a half K, and we're crossing that with 60 in the minus A direction. Alternatively, you can look at this and say, okay, this is going to rotate, and it's going to be rotation about the minus J, and then it's also going to tend to rotate the entire structure around the positive K direction. So there's two moments for each of these forces. Let's have a look. So I use 2 columns for the first half-foot bigger pulley and then 2 columns for the smaller pulley. Now, these equations solve almost immediately. Let's see how we did. Sorry, that was maybe a little fast, so let's let you have a slightly longer look at that. Then pause if you need to. When you're done looking at that, we can check the solution on the next page. So there's the answers. All right, so that is 5 equilibrium problems, and our next assignment for next week will have a number of these for you to work on. It's basically an application of our vector analysis, our vector techniques, to full-on 3-dimensional problems.